Good evening. Good evening, ladies and gentlemen. Welcome to the IEEE EPS seminar. So I think everybody already have a lot of alcohol and a drink. So I think you can enjoy this session. I'm a chair. My name is Ori from Rapidus, and also Hisada-san is a chair from Rapidus as well. So that is the EPS session is organized by TC6. TC is a technical committee. So the IEEE EPS has 12 technical committee. So TC6 is one of technical committee. So TC6 is focusing on high density and substrate on the board. So today it is, we are focusing on user perspective of chiplet technology. So we are the packaging guy. So we'd like to know some very important requirement of end users. So today we invited very much distinguished speakers over in end users team. So let me just introduce the 5 distinguished speakers. The first speaker is Iwaki-san. So Iwaki-san is the director of SOC R&D division at the Mirai Technology Corporation. So most of people is not familiar with Mirai. So Mirai is a joint company between Toyota and Denso. So now the Japanese car company is really interested in chiplet technology. So he would like to talk about this technology. And the second speaker is Raja. So Dr. Raja is a corporate vice president of packaging at AMD. So I don't have to explain it to AMD. Everybody knows AMD. Okay? So the third speaker is also come from Japan. NTT Saida-san. So the Dr. Saida is the Vice President and head of a Device Innovation Center at the NTT Corporation. So as you may know, the NTT is also the very important the player at the optical interconnection in Japan. Okay, and also the fourth speaker is Dr. Omar, is a Senior Director Engineering at Qualcomm Technology Incorporation. So I also don't need to explain the Qualcomm, okay? And then final speaker is Carlos. Dr. Carlos is a distinguished engineer in the Marvell Custom Solution Organization. So the Marvell is a very famous company, no need to explain, okay? So maybe you can enjoy some short presentation of each panelist, and also we have a panel discussion. And then finally, we'd like to get your some question to us. Thank you very much.
Okay, good evening, everyone. So thank you very much for your kind introduction, Ori-san, and also inviting me to this wonderful conference of ECTC. Actually, this is my first time to come to this conference, and I found this conference is very informative and also interactive, and also I'm very enthusiastic, so I like it. And my name is Takao Iwaki. I'm from SOCR division from Mirai Technology Corporation, and the title of my presentation is The Needs of Chiplet Technologies for Automotive Applications. First, I'd like to explain about Mirai in more detail. Mirai is a very young company, which is founded in 2020, and we are a semiconductor R&D company dedicated to both Denso, which is Japanese Tier 1, and Toyota, which is Japan's OEM. And we got basically people came from both Toyota and Denso, 250 from Denso, and another 250 from Toyota, so we have 500 people. And we've got 3 research areas. One is power semiconductors, another is sensors, and the other is SoCs. So basically, Toyota and Denso thinks those three areas are very important for future automotive applications. And this page, I'm going to explain the overview and also R&D example of Mirai's SoC team, which I'm leading. And the mission of Mirai's SoC team is basically to propose future SoC specifications to both Toyota and Denso. And not only proposing specification, but also we are doing some R&D. And I'm showing one R&D example, which is what we call visual SRAM. As you know, for autonomous driving, we need localization technique. And for localization, normally we use LiDAR, that is laser radar. But laser radar is very costly, so we decided to use existing camera to do that. But as you might be aware, to use camera for localization, we need to identify thousands of feature points from images. And actually, that processing takes very long, like 2 or 3 seconds. But we can't really wait because we are doing autonomous driving. So that's why we decided to develop accelerator for that. And I'm showing it to you. Sorry. So the left-hand side is the results of our accelerator, and the right-hand side is conventional technologies. And I hope you find the left-hand side is faster. So this is, the R&D example of our team. And from here, I'm explaining the requirements for automotive chiplets. First, I'd like to explain about levels of AD and ADAS. As you might know, there are several levels for autonomous driving. One is level 1, that is just driving support. Level 2 is partially driving assistance. And level 3 is conditional autonomous driving. And so, if the system requires driver has to take over. And level 4 is actual autonomous driving, but with limitations, basically like highway or some area of the city. And level 5 is full autonomous without any limitation. So we've got several variations of AD and ADAS. And the forecast of AD ADAS market is very promising. And we are believing in 2030, 80 million vehicles sold in the world will have some AD ADAS function. So that is almost all the cars have got some AD ADAS function in 2030. And the impact of AD ADAS advancement, we think there are 3 things. One is AI evolution. As you might know, traditionally CNN, that is normal deep neural network, is used for 2D recognition, but it's changing to transformer, which is more stable and which also can be used for 3D recognition. And in the very near future, it will change to what we call data-driven algorithm, which covers not only recognition, but localization, path planning, and even actuations. So that is almost everything about autonomous driving will be done by AI algorithms. And for that AI algorithms, which requires a lot of calculations, we need miniaturizations. And we believe in 2030, we will need 3 nanometer, 2 nanometer, or even less. And the third technology which we need is chiplet technologies. So we'll start with 2D chiplet, and then 2.5D chiplet, and then we are going to 3D chiplet. So that is our view of advancement of automotive SoCs. And I'm explaining why we need chiplet technologies for automotive applications. As I said, there are several levels of AD and ADAS, and those different levels need different types of SoCs. So, for level 1, we need small SoCs, and for level 5, we might need very large SoCs. But as you know, developing SoC is very costly, like hundreds of millions of dollars. So we can't really develop 5 or 10 SoCs for one generation. That would be like a disaster. So that's why we need chiplet technologies. For example, if we make one SoC, very small SoC, we can use it for low. And if we combine 2 of them, we can make mid-level SoCs. And if we combine 4 of them, we can make high SoCs. And if we add another SoC for accelerators, we will make, it will be premium SoCs. So we want to do like that. So, in this way, by developing only 2 SoCs, we can make 4 variations. So that's our view of chiplet technologies. And for chiplet, automotive chiplet, we need 3 technologies. One is hardware abstraction, because that is a technology which allows software engineers not need to aware about chiplet boundaries. And the second one is high-speed and reliable interface, because we want to, for hardware abstraction, we want to have cache coherency, and to do that, we want to have a very high speed and also reliable interface with functional safety. And the third one is, of course, packaging durability, which I'm explaining in more detail. And before explaining the environment of automotive environments, I need to say, for automotive applications, we believe we want to use RDL type or silicon bridge type, because silicon interposer type is too costly, so we think we need either RDL or silicon bridge type. And reliability requirements for automotive and consumer products, automotive products is, of course, very harsh. So the temperature is higher, and also the time or cycles are higher as well. And in this page, I'm explaining the challenges of mechanical reliability in automotive 2.5D packages. As you are aware, there are 3 connections about 2.5D chiplet technologies. One is micro bump, and another is C4 bump, and the other is solder ball. And all of those 3 connections are reported to be broken or cracked during some reliability tests or electromigration tests. And we need to really solve this problem. But it's not that easy to solve this issue, because silicon chip have got CTE of about 3 ppm per degree, and packaging substrates have typically 5 to 10 ppm per degree. And ECU and PCB substrate has got CTE about 15 ppm per degree. So there are a lot of discrepancies. So we need to solve this issue with very harsh automotive environments. And this is about challenges of telecommunication quality. And this is a result of ASE. So, and the top figure has got a very narrow eye pattern, eye opening. This is because the signal line is next to each other horizontally. And the second one has got wider eye opening because it doesn't have signal line next to each other, but vertically it's next to each other. And the third one is doesn't have signal line that is not placed next to each other, either in horizontally or vertically. So it has got a very wide eye opening. And actually, the line space is 2 micron and 2 micron, so that is very good. So we really need this sort of very sophisticated design for telecommunication. And the left-hand side, I have to explain about some issue. This is the graph which shows DF and DK, which is related to this eye pattern opening. And actually, we want to have smaller DF and DK to make eye pattern, eye opening larger. But this graph shows softening, as softening point increases, DF and DK values increase. That is not very good. And as you know, for automotive application, we need high value of softening point. So that is not a very easy issue to be solved. Finally, I'm explaining about ASRA, which is a Japanese Association for Automotive Chiplet Technologies. We established it on December 1st, 2023, and it contains 6 OEMs and 3 tier 1s and 5 semiconductor companies, and Mirai Technologies is one of them. And ASRA is doing not only R&D, but standardization as well for automotive chiplet technologies. So we want to solve this sort of issue with all of you here. Thank you very much.
Thanks, Ori-san, for inviting me to this panel session. It's great to be part of the 75th year of ECTC. And someone was telling me this morning, the first ECTC conference was on vacuum tubes. So we've come a long way in the last 75 years. So today, I think the focus of my brief talk is going to be how is AI hardware being enabled by chiplets, heterogeneous integration, and advanced packaging technologies, and why chiplets are sort of fundamental to what we in AMD do for AI hardware. So this chart here shows how the AI demand has been scaling rapidly, exponentially, year over year over the last 6 to 7 years. The y-axis on this plot shows floating point operations to train the frontier data systems, and how it's been scaling since like 2018 through today. And what we are seeing is across a various set of parametric models, including GPT-3, GPT-4, Llama 4, all those models, they're scaling roughly at the rate of 4 to 5x a year. And to put it in context, Moore's law's original premise was supposed to scale every 2 years, but it's scaling 2x every, 4 to 5 years maybe, or even not even that. But the compute demand that the AI industry is driving is much more exponential than that, 4 to 5x a year. And it's actually going to increase as a function over the next decade or so. So that's really the problem statement that we are trying to address in our industry. And the other part to this is, why do we build huge compute modules? I think this question has been asked by our suppliers, by our supply chain, many ecosystem partners that we've worked with. But this really gives you a good flavor of how the communication energy between different aspects of the data center scale as a function of within a piece of silicon, and within a small macro. If you talk about a register file, let's say if that is a baseline for communication or sort of the latency for a certain bit to move from one place to another. And as a function of, if you build the SoC out into a cache, it's about 100x. And if you add HBM to it, it becomes 250x roughly. And then overall, if you put it together in a package, it roughly becomes about 1,500. All the way to scale up and scale out interconnects, we are talking about 1,000 sort of orders of magnitude worsening of communication energy as we scale with distance. That's why, like, how do we maximize as much compute, as much energy efficient compute very, very locally is really going to be the key to drive these big data center systems that is driving these huge compute requirements, but how do we do it in a power efficient manner? That's the singular reason why we build these large modules. And these large modules can take different shapes and forms. Some companies build it with monolithic SoCs. We have gone headfirst with chiplets, and we'll talk a little bit more about how that has evolved over the many years. Why chiplets? Again, the other vector is, as you saw, compute demand is growing exponentially, but Moore's law is actually slowing down to the point where some functions, like the analog and memory, is actually flattening out over the last few generations. Only logic is roughly growing at the 0.85x rate, but memory is basically flattened out, and analog I/O has basically stopped scaling since the 10 to 14 nanometer generation. The right side of this page shows the cost per yielded millimeter square. The key is yielded as a function of the different nodes. And again, if you go back to Gordon Moore's original paper, his fundamental premise was the cost per transistor is going to go down. He didn't quite talk about the transistor density scaling. His fundamental premise was the cost per transistor will scale year over year. And that's clearly not happening if you look at this graph. The cost per yielded millimeter square of silicon is actually going up. So this is one of the fundamental reasons why AMD and a couple of other companies actually went headfirst in chiplets. And we've been pioneering chiplets for almost a decade now in various forms and shapes. But what's really accelerated this transition over the last 5 years or so is the use of advanced packaging technologies to be able to scale the interconnect efficiencies that we talked about earlier into sort of the next orbit, right? And it's really the advanced packaging technologies that we put in place is enabling AI challenges and Moore's law scaling, and through the use of chipletization and advanced packaging techniques, we're able to double the compute and memory gen over gen using 2.5D architectures, build energy efficient interconnects using hybrid bonded 3D architectures between different chiplets, improving the network bandwidth by improving the package losses and doing connectors. I think there's going to be a talk on optical chiplets by the NTT Takashi-san. And how do we integrate chiplets as an integrated passes, IVRs that is going to come closer and closer into the PCB and the substrate. And once we put it all together, how do you actually extract the heat out? It's going to be a key focus of the industry moving forward. And this is sort of the seminal example of what we have actually announced, MI300, which is our AI accelerator, which effectively pulls together different pieces of chiplets, all the way from the I/O die, which has an infinity fabric network on a chip along with other I/O and power functions. And then we hybrid bond either the core devices or what we call the Zen 4 cores, or the accelerator complex dies, which is really used as our AI accelerator chiplet. And in different product segments, we sort of mix and match the CCDs or the XCDs as shown here. And they all sort of talk to each other through this infinity fabric. And then if you consider what are the other chiplets we integrate, you could think of HBM as a chiplet that we integrate in a 3.5D manner, right, or 2.5D manner. So that sort of pulls all of it together on a silicon interposer, on a large substrate to build our AI accelerator products. And this trend is only going to continue accelerating as we move forward. More HBMs, more SoC to drive more and more AI compute per millimeter square to help with the locality that we talked about. One of the key advantages of going down the chiplet path is it allows flexible construction schemes or partition schemes that we can minimize or maximize the SoC utilization per a given product segment. The way we build MI300 is because it's a modular device, we are able to build two completely distinct parts. One is called the MI300A with only Zen 4 CCD cores, and the MI300X, which is our premium AI accelerator segment with all XCD cores. And in some scenarios, we're able to mix and match these CCDs and the XCDs. But more importantly, because I'm able to partition these CCD die, in terms of the memory access and the latency benefits, we can either look at this either as a single partition to a dual partition, triple partition, all the way to 8 partitions. So there is significant granularity in terms of memory partitioning, and different AI workloads require different kinds of memory partitioning. So that's one of the fundamental reasons why we were able to use the effectiveness of these chiplets for different kinds of broad workloads from training to inference. And the key elements that bring it all together is, of course, high-end 3D architectures at sub-9 micron pitch, 2.5D architectures at 35 micron pitch, 2D at 150 micron pitch, all the way down to BGA and LGA at about 1 millimeter pitch. So all these elements of the interconnect architecture are crucial to integrate chiplets at various interfaces to put together an entire system in a package. And one of the things I do want to highlight here in this panel is, just to seed some questions, is the next generation EDA and multiphysics tools are currently not there yet in terms of the level of sophistication we need for these chiplets to be talking to each other in a very coherent manner. Ideally, if you have AI-driven floor planning that allows all these chiplets to blend together in a seamless manner with a full EDA 3D place and routes so that the eventual tool flows are sort of merged silicon and package flows, along with how effectively you can do thermals, electricals, yada, yada. So all of this needs to come together from a design ecosystem standpoint. And last but not the least, especially when you're building chiplets, how do you put it all together in a mechanical fashion? How do you do the electrical fit studies to do the initial fit analysis and then sort of co-optimize it from a performance optimization? It becomes extremely more complex when you have multiple chiplets. So driving these design ecosystems to do early feasibility studies is also going to be absolutely crucial. And with that, I think that's the end of it. Thank you.
Thank you, Sada-san. Thank you, Ori-san. Good evening, everyone. I'm Takashi Saida from NTT. First of all, congratulations on the 75th anniversary of ECTC. This is the first time for me to attend this conference, as I come from optical technologies. And my home conference has been the OFC, Optical Fiber Conference, which celebrated the 50th anniversary this year, early this year. And OFC has a rich history, but ECTC has more. And for the past decade, I have felt that the collaboration of optical technologies and the packaging technologies is of increasing importance. And today I'd like to talk about one of such a collaboration, optical chiplet integration. Here is a kind of the rule of thumb graph. The horizontal axis shows the reach, and the vertical axis shows the capacity per channel. As can be seen here, that we introduced the fiber to the phone in 1981. The speed was only 32 megabits per second, and the distance was several tens kilometers. But at that time, the optics did make sense comparing with the electronics technologies. And we installed the optical technologies for 1 gig, 10 gig, and let me show you. And here is the rule of thumb curve. It's the 100 gigabit per second times meter. So in future, we will use the optical technologies even for less than 1 meter. And based on that idea, we have established the PEC device roadmap. PEC means photonics electronics convergence devices. We made it in 2020, and we categorized the 4 PECs. PEC1 is for long haul and metro and data center interconnect. We have already commercialized it, and now it's available from our subsidiary, NTT Innovative Devices. And currently we are working on the PEC2. PEC2 is an interboard communications, and the target is this year. And actually, currently we are having the, we have already demonstrated it in the Osaka Expo in Japan. And the next target is the PEC3. PEC3 is inter-package optical links. and the key device is optical chiplet. And PEC-4 is the future stuff, but it will be the inter-die links with very high-speed communications. Today, I'd like to talk about the optical chiplet. Here is a use case of optical chiplet for GPU scale-up. This is we call it unit cell. It is based on the package substrate, and the size is 100 meter by 100 meter. And it has the 4 GPUs and 4 optical chiplets. And inside the unit cell, of course, the interconnect is in electrical. But beyond that, we use the optical interconnect. Here you can see the 8 unit cells here, and here is the optical switch, 8 array, 8 by 8 reconfigurable optical switch. So you can connect any chiplet to any unit cell to any unit cell by using the optical means. And this shows the enlarged view graph. The left-hand figure shows that the GPU package is a mock-up, but the middle figure shows the optical chiplet prototype. And here we have integrated the TX and RX, and also the EIC, TIA, and drivers. They are embedded in the substrate. And we demonstrated the 64 gigabit PAM4. And the key here is we use the membrane photonics. Membrane photonics is based on the inch MOSFET, but the usual conventional laser has been made by depositing the different layers. So size is very large. But we use the membrane layers, and like a CMOS, we change the N layer and P layer by doping. Here shows the inch MOSFET-based membrane photonics technologies. As I mentioned here, we use a very small active regions by using the membrane photonics technologies. So when we make lasers, it's very energy efficient because the photon and carrier are confined in a very small region. Also, the size is very small, so it means that the low junction capacitance. So we can drive EAM at a very high speed. Can we see here? The bandwidth, 3D bandwidth is more than 100 gigahertz. And the dimension of the membrane photonics is very similar to the silicon photonics. So we can easily couple from membrane photonics to silicon photonics or vice versa. And this shows the feasibility evaluation as regards power efficiency. We integrated membrane EA electrical absorption DFB lasers here, and we made the membrane photodiodes here and connected by SIX waveguides. And this shows the membrane EFB laser configuration, and this shows the membrane photodiode configuration. The basic configuration is almost the same, but except for the lasers. And can we see here that we tested 2 conditions. One is a 64 gigabit NRZ, and the other one is a 50 gigabit per second NRZ. And energy efficiency was 0.26 picojoule per bit and 0.14 picojoule per bit. We reported it in a OFC conference this year. Okay, in summary, we came from the communication community, optical communication community, and we really think it's important to collaborate with the electronics package community. And we would try to bring our optical technology to the computing world with a collaboration with you. Thank you very much.
Okay, thanks everybody. Appreciate you joining late in the evening. And thank you first to the ECTC Packaging Committee and to Hisada-san and Ori-san for the invitation to speak tonight. Tonight, of course, we're talking about chiplets, and what I'd like to do is dig a little more into the technology to enable very high I/O per millimeter escape density. And specifically, I'm going to talk about 2D organic substrate versus 2.5D technologies and where they can really work together to drive the technology in a cost-effective manner moving forward. So I'll go through first a quick definition, 2D, 2.5D, to try to keep it simple. I'll then go through some examples of the technologies. I'll talk through some escape routing trends, and these are my projections for different technologies. And then at the end, I'll cover the paths forward. Okay, so first, just to make it easy tonight, I want to have only two categories, 2D and 2.5D. I'm aware that there are different flavors, 2.1, 2.3, 2.7, 2.9. 3D, of course, is TSV-based. But what I'd like to do is just focus on 2D for tonight, meaning die attached directly to the organic substrate. And then in the case of 2.5D, it's where we have what I'll call a high-density routing layer inserted between the active die and the organic substrate. So this could be RDL layers on the die side. It could be RDL layers on the substrate. It could be silicon bridges embedded in the substrate as well. But I'll just try to keep it high level with these two categories for the rest of the talk. Okay, so first, 2D technology, everybody's aware if you have chiplets in a 2D interconnect, essentially what you're doing is taking the chiplet die, you're assembling them onto the substrate and doing the subsequent steps. But in the case of 2.5D, of course, it's a little more complex. And I also want to separate substrate-based 2.5D and die-based 2.5D. So I'll go through a couple of examples of substrate-based first. This is where the high-density routing layer resides on the organic substrate side. So the first example here is ITHOP, which is from Shinko, and they place the, actually it's two substrates. There's a photoimageable-based substrate that's placed on top of the regular FCBGA organic substrate, and then we do the assembly in an underfill. The next is where we actually take the high-density routing layers and insert them into the substrate itself. And this example would be EMIB from Intel, where, for example, there's a silicon bridge here that's connecting them. And so these two are what I'll refer to as a substrate-based 2.5D. Next is the die-based 2.5D, and this is where the high-density routing layers are on the die side. So the first is chip first, where you start with the die and you build the high-density routing layers directly on it, and then that entire interposer would be assembled onto the organic substrates. And then the last is the chip last example, and this is the HBM-friendly version, where you actually have the organic substrate on the bottom, you have a high-density routing layer in between, onto which the chiplets are first assembled, and then that entire thing is assembled onto the substrate. So these are widely different technology options that we have available today. And so the key question is, how do we decide which one to use, and how do we compare them? So what I will do is use I/O per millimeter per layer as the metric to compare these, and I'll show some information along those lines going forward. Okay, so let me explain a bit about this slide. At the top left, this is meant to show from a top view what a typical escape routing scenario would look like on a substrate. So we would have copper pads with bumps. The red arrow would be the minimum pitch that's capable in the assembly process. The blue arrow is the escape routing pitch. So this is the pitch through which you're able to escape traces. And the item that we're most concerned about is in the blue box here, which is how many I/O can we escape per millimeter. And so in the substrate case, we have a certain number that I'll get to. In the high-density routing layer case, it's the analog over here, just with different colors. But the actual magnitude of the I/O per millimeter is much different. So in the middle here is a graph. On the y-axis is the I/O per millimeter per layer in the escape region. And on the x-axis is the HVM year. So what you'll see at the bottom is a blue line. And this blue line is just the 2D substrate, so where you have die directly on an FCBGA substrate. And today, the I/O per millimeter number is roughly 15. If you compare that to the different 2.5D options, So for example, an RDL-based solution, EMIB, ITHOP, these are up in the 160 IO per millimeter plus today, so much higher density. So there's about a 10x delta between where we are with substrate today and the 2.5D. So what I would like to do is push to continue the development of the 2D substrate technology so that we can close this gap to some degree. So one of the things that comes up regularly is the question of whether 2.5D will cannibalize 2D or vice versa. At this point, I don't think either will cannibalize the other. They'll continue to exist together and have to work in a complementary fashion. The question will be, how do we get to the most economically viable solution by using them together? So this is a busy table at the bottom, but I'll walk through what it contains briefly. So what I've listed here are the key factors that play into the calculation of IO per millimeter. There's minimum pitch, minimum trace width and space, and then ultimately the IO per millimeter number, which is the blue box. So today for the 2D, as I mentioned, we're at about 15 IO per millimeter. And I'm projecting that if we, over the course of the next few years, are able to drive down the pitch roughly from 90 to 60, and the line in space from 810 to 22, we could get an almost 10x improvement, so up to 142 IO per millimeter. And so on the right are 2.5D examples, and I need to give a couple of caveats here. The first is the numbers that I've included in the table. These are based on literature searches, information I've been able to extract. I'm aware that some of these numbers are not the latest and greatest, but I have to respect NDAs, so I was careful with what I placed in the table. The second item is, please note that I'm not advocating for one 2.5D solution over another. This is just me trying to compare, and really what I'm advocating for is to continue the 2D development. So what you see today is, as I mentioned, the 2.5D examples were in the 160 plus IO per millimeter. This over time is going to continue to go up, probably in the range of 500 IO per millimeter, if not more, in the next few years. Okay. So this is the same chart again. And what I would like to just point out is that I think there's a general perception in the industry that as we adopt 2.5D, we'll put all of the heavy-duty routing on the 2.5D, and the substrate can be relegated to a very coarse pitch, very low-cost substrate. But actually, that's not turning out to be the case. The economics are driving us in a different direction. So today, this is kind of the mindset that we can put all the routing on one side and make the substrate low cost. But I believe if we move forward and in this red box here really drive the routing capability of the substrate itself, we can offload some of the routing from the HDRL into the substrate. And the reason for this is the cost. The cost of the 2.5D technologies is still very high relative to the 2D substrate. So I think it would be wise for the industry to move in this direction to help us to rebalance the routing and the cost equation here. Okay, and then lastly, on paths forward, in the 2D space, as I mentioned, we'll need to continue to drive the pitch, pad sizes, minimum lines in space, et cetera. This is going to require a lot of focus from the substrate manufacturing. Patterning is going to be key, so we need investment in next generation patterning. So this means equipment, process, new clean rooms or clean room upgrades. And then from the core material itself, we need the panels to be very flat to enable proper lithography yields. This means we can look at further reducing CTEs, trying to find new organic materials that are flat, perhaps moving to glass in the core or even silicon as the material for the core. And then on the assembly side, both assembly and chip package interaction-wise, we have to adopt chip attach methods that will allow us to get to finer pitch, and we have to find ways to try to buffer the stress. One thing I didn't mention is that to get the pitch down for assembly, you have to reduce the diameter of the flip chip bump on the die. That has a chip package implication. So in order to shrink those bumps, we have to find a way to dissipate that stress so that we don't crack the ELK at the back end of the die. And then in the 2.5D space, obviously, if we can move from a 300 millimeter round wafer solution into some larger panel, that will help us to drive down the cost of these technologies. And in addition, assembly will have to continue to adopt new methods to try to get to a finer pitch. That was it. Thank you.
Hello, ladies and gentlemen. I'm a silicon architect surrounded by packaging people. So this is not going to end well. So here's the thing. I'm here to present to you what is my need in the hope that you will be able to deliver to me the solution. Okay? So let's see how that goes. Now, part of it is the fact that nowadays I honestly believe that the distinction between silicon design and packaging design is actually quite artificial, in the sense that it's so intertwined and so interdependent that either we think about it at the system level and how do we solve the system need by using both approaches, or we basically will not be able to succeed. However, the point of this seminar was to think about the user point of view. So the first thing I asked myself is, who the heck is the user, right? Because, you know, when you think about it, if we're thinking about chiplets and what chiplets change in the ecosystem of how do you design your systems, once again, emphasis on system, who is the user? Is it the company that buys the chiplet? Is it the architect, such as myself, that uses chiplets as one of the building blocks in the system? Is it simply the customer that buys the entire system and all of a sudden has this diversity of providers that make maybe the accountability chain a little bit harder to follow? And when something fails, you know, it starts to get complicated to know who is responsible for what. So actually, I couldn't come to a conclusion, so I decided to present my own point of view as a silicon architect. And since I am a silicon architect, I want to make it very clear. I do not like chiplets. Okay? And the reason is very simple. I do not design with chiplets in mind. What I do is building blocks based on functionality, right? So what is important to me is which block is connected to which block in which way to perform which function. I do not necessarily think in terms of the physicality of it or how many silicon blocks and how do they interconnect. In fact, that is a huge nuisance to me, right? I would like to have a lean, monolithic, homogeneous system. So if you look at this diagram here, that is kind of a cartoon representation of a basic router. If I think that I need more silicon space, which I always do, obviously, and I think about partitioning it, I mean, it's not evident, right? It's not just like I take my system, I divide it in 4 pieces, and I'm done. This is not how I would partition a chiplet. And if you think about how a silicon architect thinks about these block diagrams, at the end of the day, what you have is a series of functions of blocks that are interconnected by means of some sort of on-die bus. And it can be AXI, or it can be some NOC, or it can be CHI, or it can be anything else. But ultimately, we have kind of a flat view of our system interconnected by on-die buses. And what we really would like to do with chiplets is the ability to make them transparent, the ability to expand that on-die bus across the physical boundaries without having to pay any attention, and certainly without having to pay any price for doing so, right? So where do we pay a price? Well, certainly in the die-to-die interface, right? We have a big PHY that costs a ton of area, and it burns a ton of power, and it provokes a protocol adaptation because, as I said, I had AXI originally, but now I have whichever die-to-die interface. Let's say UCIe. Now I need to adapt my AXI to UCIe, cross across the chiplet, and convert again to my original protocol. I don't like that. It brings in complexity, it brings in latency, it creates semantic differences that I don't care about, right? So ultimately, what I would like to do is to remove it entirely, right? I would like to not see a die-to-die interface. What I need is flop-to-flop connectivity across the dies, right? And then I have, you see, a transparent view across the physical dies, and I don't have to pay a penalty. And that's where I'm asking you, gentlemen and ladies, to help me, right? Is what can you give me? How do you make this happen, right? And so how do I get that flop-to-flop connectivity and equivalent density to my on-die bus? Equivalent latency, equivalent density, that is what we need from the packaging community. And certainly, there is very promising solutions emerging in the area, for example, of hybrid bonded interposers and similar solutions that are kind of getting there, but are not completely mature enough, are not maybe yet transparent enough. Think about 3D. 3D is the big promise that we are going to achieve that flop-to-flop connectivity that I'm talking about. Well, guess what? It's not as simple as that, is it? Right? It's not that easy to really achieve that flop-to-flop connectivity, even in 3D, let alone in, say, chiplet-based structures. So, again, as the silicon architect that presents himself here as the user, my ask to this community is, what can you give me, right? How do we together make these chiplets truly transparent, right? And there is certainly other aspects that as a user I would like to, that are not as package-centric. For example, as a user, I'm very concerned about the boot sequence. And that has nothing to do with packaging, right? But when I have chiplets in my design, I need to make sure that they fit into my sequence of boot in my system. And the problem is, typically the way you manage that is because you control the entire boot sequence. But now I'm buying chiplets from a third party. How much influence do I have over how boot happens in the chiplet? How much influence do I have how the secure boot happens in the chiplet, right? How much control do I have about the management interface to the chiplet? Because, again, I'm building a system. I'm not just building a collection of independent pieces. So those aspects are also of importance to me as a silicon architect. So I'm not expecting you people to be able to solve that, but if you can help me to get rid of the die-to-die interface and make it truly transparent and help me extend my on-die bus across the chiplets, I would be tremendously thankful. So in that sense, thank you very much. Now, let's not forget one last item, is, you see, the market has this tendency to create barriers, so that if you adopt one solution, well, maybe you cannot adopt another solution so easily. Like, for example, different packaging technologies will present barriers in terms of what your minimum pitch can be. Well, whenever you gentlemen and ladies are thinking about building this fabled transparent chiplet that I'm asking for, please consider that it needs to be applicable to any 2.5D technology out there. In particular, please do not constrain me in the bump pitch that I can use. Make it so that I can use whichever solution you come up with across a variety of bump pitches, and you know, remind your chiplet designing friends when they do so. And in that vein, thank you very much.
Okay, so we had all presentations, so we move on to the panel discussion. So thank you for the interesting talks. So chiplet gives us freedom and complexity of the package, especially for design. And, I think the package design depends on the application. And, the question I want to ask
is what is the key enabling factor of the chiplet, and what is the critical, the biggest critical point for the challenge. So I want to ask this question for the automotive application space to Iwaki-san, and HPC application space for Raja-san, and communication space for Saida-san. So Iwaki-san, what is the key enabling factor and most critical challenge for your application, automotive application?
Right. Well, actually, there are many enabling factor for automotive chiplets. So, there are several things. One thing is about standardization, because for automotive applications, and we might want to use different SoC vendors, SoCs for chiplet technologies. So, in that case, we want to know how to connect each SoCs each other. It's not that easy. So we might want to define the interface, like physical layer, die-to-die adapter layer, protocol layer, and so on. And also we want to know how to, boot the SoCs, or how to control the power consumption. The temperature of each other, or how to test. So there are many things which need to be standardized. But from the point of view of packaging technologies, I think the most important thing is, we can explain, what's happening about reliability, because we can't really use packaging which just pass reliability tests, because for automotive applications we really need to ensure the quality assurance is very important, and in that case we can't really say this product just passed the reliability test, but we need to really design the reliability. In that case, we want to know the mechanism why this packaging is broken at this temperature, and why it's not broken at this lower temperature. And we really need to know the mechanism and theory to really design the reliability. So that's what I'm expecting from this sort of chiplet packaging conference. So that is the enabling factor, I think.
Okay, thank you. So you used. Oh, okay.
So just one more very simple question to Iwaki-san. So you showed this kind of a roadmap. So beyond the 2 nanometer, you will use in the future. So you said it's some kind of a miniaturization. Actually, what is the motivation? That miniaturization, or the performance, or the reduces the power consumption? Why you would like to use the 2 nanometer technology?
So my answer is both of them. So performance and lower power consumption. And as I explained, the AI and algorithms is evolving day and day, and it's getting larger and larger. So we really need, and that sort of, very large volume, very high performance SoCs. So we need to achieve that. We need very narrow, small, fine pitch, small nodes, like 3 nanometer, 2 nanometer, or even beyond that. And also the power consumption is of course very important. So both of them.
Thank you. So for the high performance computing application, what is the most critical challenge?
I think the key enabling technologies in the HPC space is really geared towards optimizing for power, performance, area, and cost. So advanced packaging technologies, all the way from 3D, 2.5D, 2D, and even PCB technologies, they're all crucial and enablers in getting to the right PPAC targets. And then the other point in all of the spaces, including automotive and HPC, is how do you get the known good die across the entire stack? Is it truly known good die, or is it partially known good die? What are the communications between the different parts of the ecosystem that truly communicates the known goodness of the die? How do we test it at different levels of the stack? Those are all going to be the key enablers.
Yeah, thank you. Okay, for the communication application space, what is your thought, Saida-san?
As regards the optical chiplet, I think the key enabler will be the innovation of the ecosystem. When we install the optical technology to the electronics, we need to think about the reliability, as Yoaki-san mentioned. Also, that we need to think about how to maintenance it, how to repair it. The usability or the serviceability will be the key. And it reminds me the history of the fiber to the home. When NTT installed the fiber to the home in 2000, I think 2000, around 2000, at that time we need to, educate the engineers how to repair the optical fiber, how to install the optical fiber. So we need to renovate the ecosystem as a whole.
Okay, thank you. So for Mao-san, I want to ask a different question. So I think, sorry. So for the chiplet, I think the die-to-die interface is one of the biggest, most important technology factor. And so for better usability of the chiplet, what is the missing piece of the die-to-die interface from your perspective? Like, process technology or design methodology or testing of the connectivity between the chiplets. So what is most important for the die-to-die interface?
Okay, I think you touched on several things.
Sorry.
But yeah, I would say it depends on why we're going to chiplet. So for example, in my mind, there are three reasons. One is you have a very large die and you want to break it into smaller die to manage the defect density yield loss. In that case, you would need to have, I believe, if you want to have your own custom silicon, an internally designed block to communicate between the two die that's optimized for that communication. The second reason would be if you have the need to disintegrate your monolithic die from a cost standpoint to have multiple die nodes in the same package. That's where the challenge comes, I believe, with the interfaces, because you are going to have to manage different interfaces from different nodes. And I think the escape routing piece and the signal integrity part are going to be very difficult. One of the key problems with going to chiplet, in my view, is you could see when I shared my slides, there's a pressure to go to 1.1, 0.8, even lower line in space. For these long distances between the chips, the insertion loss and the crosstalk are going to be a huge headache long term. So we have to find a way to overcome that. So I think it's kind of a mix of things in play. And I think, I didn't touch on the third one. The third reason to go chiplet, I believe, is thermals. So thermals is a big challenge, not only in HPC, but in automotive. And I think if the die can be disintegrated and re-architected so that the heat flux can be smeared out, so to speak, among multiple chiplets, that would be another reason to do it.
You mean some crosstalk between the chips?
No, thermals. So if you have a very high watts per millimeter square dissipation, if you can break that, the sources of heat, the hotspots, into multiple chiplets, it can help you to manage them.
Okay, thank you. So, Carlos-san, I understand that you don't like die-to-die interface. You want to remove it. So to do that, how can you do it?
Well, magic would help. But other than that, again, we have developed hybrid bonding as a 3D technology that seems to be very promising in terms of density, low latency, very low power consumption. So the extension of that concept to hybrid bonded interposers, for example, is something that seems to me to be very promising because it extends that magic, really, really minimum die-to-die interface from the 3D architecture, which brings its own problems, for example, thermals, as we all know, to a more traditional 2.5D architecture, right? So everything we can do to approach that concept of extremely simple, extremely low power, extremely low latency die-to-die, such as hybrid bonding connections to the 2.5D space, I think would be extremely valuable.
So I think some the architecture people they don't like the chiplet. That is a very important message for the packaging team. So of course we respected that you mentioned, but we have to find a kind of a compromise because of the cost. So the chiplet is really good for the casting, but maybe we kill the kind of performance. But finally, the 3D interconnection, then we can reduce the distance. So the 3D is a very good way to increase in the performance. But the 3D is thermal is a very much issue. So that is a little bit difficult in the logic to logic in the connection 3D. But we have to discuss it much more with the architecture people, and then to find a very good solution. So I very much like your team don't like chiplet.
Okay, so it's time for the Q&A. So we want to accept questions from the audience. So, so mic is over there. So please step to the microphone.
So I have a question too. So chiplet is the non-good die is a very important. A lot of a chip is getting together. So on the other hand, many chips. So maybe we have to consider kind of redundant some circuit architecture or the kind of rework or repairing method to improve the use. Do you have any idea?
It's a good question, Rizan. It's redundancy as well as repairability are ideal case scenarios. But when we start putting these features in logic, it starts compromising on the performance significantly. It's much easier to put redundancy in memory or FPGA devices, but when you go CPU or GPU logic, that becomes a very slippery slope in terms of the overall end-to-end architecture that we're shooting for. So the reality is, in the logic space, you have to figure out how we can improve test methodologies designed for test features that can truly bring known good die. It's not something that you can just solve with more redundancy. Right? And to Carlos's point, I was a silicon architect, and now I consider myself a system architect too. Nobody likes data interfaces. We live with them, right? So, and fundamentally, everybody's going chiplets because Moore's is not helping us. It's not like everybody wanted to do chiplets. So it's really something that, as a community, the silicon folks have already been partnering with what you call packaging architects or system architects. But it's really the co-optimization or the system technology co-optimization that we should be focusing on as an industry, as opposed to, hey, I'm a silicon architect and you're a packaging person, I do what I do, package does what it does. It's not the scenario anymore. Right?
Thank you. So is there any questions from the audience?
Thank you all for the enjoyable talk. So, yeah, as a packaging guy, I do want to say the packaging guys didn't start this chiplet thing, right? It was in response to a requirement. But given that, you know, if you want these really light, thin interfaces, but yet you also need to be able to make these connections, that would imply you at least need bumps and things lined up in the proper place. Or you disable, I guess my question is, given that, is it possible to develop this open chiplet ecosystem that people are envisioning, or is it always going to stay fairly vertical because of the needs that you've highlighted, Carlos?
I think it depends a little bit also on the area of application, right? So, for example, in the area that I know best, which is data center, extremely customized, very large, very complex systems that are pushing really the bleeding edge of technology, there is an extremely strong desire for optimization. And as such, it's difficult to envision the usage of chiplets outside of families of products, right? So when you're building your family of products from the simpler configuration to the more complex configuration, for example, you can think about which building blocks you need and how you're going to combine them so that there is reuse. And you can also think about how you're going to assemble them and think about the packaging strategy that you're going to follow so that it maximizes that optimization. And that's what I see in the market today. A truly open chiplet, say, ecosystem that is purely interchangeable. I have difficulty envisioning that in this scenario of high optimization, but maybe in a scenario where performance is not everything or customization is not everything, it will become simpler. I would expect that in that scenario, we don't need the degree of minimalization of the die-to-die interface that I am talking about.
I do concur with Carlos on this point. I think it's a noble goal, standardizing chiplets, standardizing interfaces. But if you step back and think about what standardization really means, is catering to 100 different users, which means the interface by definition is bloated. So I do agree with him, right? Like in the high performance space where every millimeter square, every watt, every milliwatt matters, people are going to customize, right? So I think it's going to be use cases where, for example, there's some novel technology, I don't know, quantum comes up and nobody in the HPC AI space does quantum. There's a startup that does quantum and then we want to integrate it. Maybe that's a use case where we might be okay with standardization. But for practical applications, I don't think it's there yet.
If I can extend on that. So, I mean, we came from a place where, you know, we were designing monolithic die, and then those die started to be made up of different third-party IPs. So we did manage to reach a point where we could bring in other design elements. Now we're just talking about doing that tough word, but bringing in harder elements rather than just soft IP. So are there pieces that you can see that could become chipletized, say SerDes interfaces or compute blocks, something like that? Or does that, again, because of the performance limitations, really become very user or designer specific?
I think if the chipletization is always generally the right direction, depending on how quickly you're adopting the latest node, right? The question you're asking us is sort of two different things. One is, hey, could we chipletize a different piece of block? The answer to this is yes, if I can design a die-to-die interface that can solve my power performance area and cost problem and get the best performance per watt holistically, even if I chipletize versus a monolithic. The key is power performance area and cost. The C matters. Because what the customers pay for is performance per dollar, right? So that's really the key. We will, as long as it satisfies this general boundary condition, we should be okay.
Okay. Thanks.
Thank you for the wonderful talk. I learned a lot today. I had a question about the general AI accelerator systems that we see today, where you have a CPU, you have a GPU, you have HBM die. Is there a general trend where CPU to CPU connection is more important or a bottleneck compared to a GPU to HBM interface? And if that is true, does that mean that you don't need, let's say, to maximize the number of wires by reducing the pitch and the line space size of those wires, versus maybe keep them fat because the signal integrity is more important? If those are the considerations, do you think a particular packaging technology, meaning silicon-based interposer or RDL, which can give you these different combinations, will be better suited? So first, I don't know if that is a requirement. And second, if that is true, then do you see a particular packaging technology being more suitable for these applications?
Complicated question, if you ask me. Let me answer in a maybe slightly different way. What do I believe is one of the primary drivers of integration in the data center? It's certainly scalability of the system, right? So if you think, for example, about AI, the big issue with AI is that the system is much bigger than what silicon can contain in one piece, right? So you're trying to put as many of those pieces together as you can. And the issue with that is that, in particular in the area of AI, the amount of data interchange between those pieces is huge, right? So in that context, you definitely need the maximum density that you can achieve, as well as the minimum latency. I don't see a compromise that is possible there. Again, in other areas of application, probably your constraints are different, and you can reach different points of optimization.
I mean, if you look at a data center rack infrastructure, yes, the GPU to GPU within rack infrastructure or communication is important, but rack to rack, you still have to go through copper wiring on the PCB and cables and all of that. So we don't look at it as, hey, this core needs to talk to this core fast. It's an overall infrastructure rack level optimization is what we typically shoot for, and whatever gives you the best efficiency in that level is, there are different trade-offs. Sometimes it's GPU to HBM for some workloads. Sometimes it's GPU to GPU. Sometimes it's this GPU on this point of the rack to this GPU on this point of the rack. So it's all needs to be optimized together.
And just to add to that, I think the cost is also very key, right? So the cost per layer for whichever I/O per millimeter you're chasing is what we have to get to. So whether it's 2D, 2.5D, or 3D, that will ultimately be a major factor in the decision that we make, because that'll determine how many layers we need and then where the cost goes from there for the overall package.
Thank you.
Okay, so this will be the last one.
Okay, so my name is Hideki Sasaki, Rapidus Corporation. My question is about design environment. Design environment for chiplet. So how do you feel about our recent design environment is enough to realize a chiplet? For example, is a design tool, a simulation tool, a design kit or something? The question is for all panelists.
Thank you very much. My personal answer is no. One of the issues that I see today is that EDA tools come from two different worlds, right? So you have your traditional silicon tools and you have your traditional packaging tools. And again, I don't see the distinction anymore as a system designer, right? So I would love to see my EDA tools integrated in such a way that they can co-design entirely. I think we are trying to get there. I don't think we're there yet.
So,
Personally, my answer is, the EDA environment now is not good enough because, actually, the technology is advancing day by day. So, EDA cannot be good enough. And, I mean, it can't be good enough because technology is advancing day by day. So that's what I'm thinking. And for example, immunized technologies, we are doing some die-to-die telecommunication analog simulation, that is signal integrity. And we are doing this simulation, and we get some results. But actually, we use several different tools to do the same simulation, and those two or three simulators give us different results. So that means we can't really tell which one is really correct. So we need to, do some the actual evaluation to tell which one is correct. So at the moment, I don't think it's enough to do designing by simulation only. So that's why I think so.
Thank you very much.
So that's the last question to the Saida-san. So the CPO is a kind of right now the mainstream. So the packaging, the ECTC is also that we had a lot of discussion about the CPO. So what is the next is the CPO?
I think that there is some several definitions regarding the CPO. Our chiplet is a kind of CPO, but we believe that our optical chiplet, very close to the die, will be the next step of the CPO.
So the NDT showed the sound, the chip-to-chip connection is also you are thinking the optical, and also the inside chip is also you are thinking the optical, right?
In the future, yes.
Okay, thank you.
okay, thank you. So now the time is up. So I want to conclude this session. So let's thank speakers. Thank you very much. Everyone, thank you for coming. Okay, thank you very much.